Implementation of 4D error correction codes in quantum computing by Q4 2024. Overview. The implementation of 4D error correction codes in quantum computing represents a transformative step in the field of quantum information science. Targeted for completion by the end of Q4 2024, this ambitious project will unfold over 3 phases supported by a $5 million research and development R&D budget. The initiative involves collaboration with 8 leading universities aiming to bolster the reliability and efficiency of quantum computing systems, which are critical for advancing technologies across various sectors. Phases of implementation. Phase 1, Research and Development Q1 2023, Q2 2024. The first phase emphasizes foundational research and theoretical exploration. Key objectives include theoretical foundations, establishing a comprehensive understanding of 4D error correction codes and their potential to mitigate errors in quantum systems which are highly susceptible to noise and interference. Simulations, conducting initial simulations to model the behavior of these codes under various conditions, thus assessing their efficacy in real-world quantum computing environments. This phase involves a multidisciplinary approach bringing together experts from quantum physics, computer science, and applied mathematics to explore the theoretical aspects of error correction. Phase 2, Prototype Development Q3 2024. Following successful theoretical and simulation work, the second phase focuses on practical implementation through prototype development. Prototype Quantum Computing System, developing a prototype that integrates the 4D error correction framework. This prototype will serve as a testing ground for the new codes in a controlled environment. Rigorous testing, implementing extensive testing protocols to validate the effectiveness of the error correction codes, ensuring they perform reliably under realistic operational conditions. This phase is crucial for transitioning from theory to practice, providing insights into the real-world applicability of the developed error correction methods. Phase 3, Full-Scale Implementation and Evaluation Q4 2024. The final phase aims to deploy the developed system for practical applications and conduct a comprehensive evaluation. Deployment, implementing the error-corrected quantum computing system in various use cases to demonstrate its capabilities. Performance evaluation, analyzing the system's performance, focusing on improvements in computational accuracy and efficiency compared to existing quantum computing systems. This phase will provide critical insights into the operational advantages offered by 4D error correction codes, paving the way for more robust quantum computing applications. Collaboration with universities. The project is distinguished by its collaborative nature, involving 8 renowned universities. This partnership is designed to leverage a wide range of expertise and foster innovation. Expertise sharing, universities will contribute knowledge in quantum physics, computer science, and applied mathematics, creating a rich environment for academic and practical advancements in error correction. Innovation hubs. The collaboration will establish innovation hubs where researchers can share insights, conduct joint experiments, and explore new methodologies for error correction in quantum systems. This collaborative framework is critical for addressing the complex challenges that arise in the development of scalable quantum computing technologies. Potential applications and use cases. While specific applications are still being defined, the successful implementation of 4D error correction codes can significantly impact various sectors. Quantum cryptography, enhancing security protocols for data transmission, making quantum communication more reliable against eavesdropping and cyber threats. Advanced materials modeling, facilitating breakthroughs in industries such as pharmaceuticals and renewable energy by enabling accurate simulations of molecular interactions and material properties. Optimization in logistics and supply chains, solving complex optimization problems that traditional computing methods struggle with, leading to more efficient logistical operations and supply chain management. These applications highlight the transformative potential of 4D error correction codes, positioning quantum computing as a critical tool for future technological advancements. Key insights and conclusions. Importance of error correction. Across multiple sources, the significance of error correction in quantum computing is underscored as a vital component for achieving scalable and reliable quantum systems. Error correction is essential to maintain the integrity of quantum information and ensure the functionality of quantum algorithms. Collaborative approach. The emphasis on collaboration with leading universities illustrates the necessity of diverse expertise in addressing the intricate challenges faced in quantum technology development. This collective effort promotes knowledge exchange, innovation, and the establishment of best practices in the field. Variability in technical detail. Different sources present varying levels of technical detail regarding the implementation of 4D error correction codes. While some focus on a broad overview suitable for a general audience, others delve into intricate technical discussions catering to specialists in quantum computing and error correction. Timeline of events. 2023. Project initiation with Phase 1 centered on research and development, focusing on theoretical frameworks and simulations. Q2 2024. Completion of theoretical work leading to readiness for Phase 2, where prototype development begins. Q3 2024. Development and rigorous testing of the prototype quantum computing system integrating the new error correction codes. Q4 2024. Full-scale implementation and performance evaluation, demonstrating the advancements in quantum computing capabilities and the effectiveness of the 4D error correction codes. Final thoughts. The implementation of 4D error correction codes in quantum computing is a groundbreaking initiative poised to overcome significant barriers in the field. By enhancing the reliability and efficiency of quantum systems, this project could transform numerous industries that rely on advanced computational techniques. The collaborative efforts among leading universities and the structured phases of development will ensure a comprehensive approach to solving one of the most critical challenges in quantum computing today. As the project progresses, it will undoubtedly contribute to the ongoing evolution of quantum technology, paving the way for a new era of computational power and capability. The implementation of 4D error correction codes in quantum computing presents several counterintuitive insights that challenge conventional understanding in the field. Here are the key counterintuitive points identified in the provided content. 1. Complexity versus necessity of error correction. While error correction is often perceived as an additional layer complicating quantum systems, the implementation of 4D error correction codes suggests that such complexity is not merely necessary but vital. The counterintuitive idea here is that the seemingly complex systems may actually simplify the path to achieving reliable quantum computing. By embracing complexity through advanced error correction, researchers can potentially enhance the overall functionality and stability of quantum systems. 2. Budget allocation and collaboration. The project operates under a $5 million R&D budget, which might seem modest in the context of high-stakes quantum computing advancements. This raises the counterintuitive notion that significant breakthroughs can emerge from relatively constrained financial resources, challenging the assumption that only well-funded projects can lead to substantial innovations. The collaboration with 8 leading universities further emphasizes that leveraging collective expertise may yield more significant results than relying solely on large financial investments. 3. Phased implementation strategy. The structured 3-phase approach might initially appear to slow down progress due to its segmented nature. However, this methodology reveals a counterintuitive advantage. Breaking down the complex process into manageable phases allows for iterative learning and adaptation. Instead of a singular overwhelming push towards implementation, gradual progress through research, prototyping, and evaluation may lead to more robust and informed outcomes. For broader applications beyond quantum computing, the potential applications mentioned, such as in quantum cryptography and materials modeling, suggests that error correction codes might impact various sectors beyond the realm of quantum computing itself. This counters the intuitive belief that advancements in quantum technology are only relevant within the confines of quantum computing. By enhancing error correction, the project may inadvertently facilitate breakthroughs in other fields which are often overlooked in discussions focused solely on quantum computing. 5. Collaboration dynamics. The collaboration with 8 universities could be seen as a dilution of focus where multiple entities working together might lead to complexity and inefficiency. However, the counterintuitive outcome is that this diversity of thought and expertise could accelerate innovation by incorporating varied perspectives, ultimately leading to more comprehensive solutions. This challenges the standard notion that fewer collaborators often mean more streamlined and effective project execution. 6. Error correction as a pathway to scalability. While error correction is often regarded as a technical hurdle, the project posits that it is actually a pathway to scalability for quantum computing. This flips the conventional view that error correction is merely a necessary evil. Instead, it presents an opportunity to develop scalable systems that can handle larger and more complex computations effectively. 7. Impact of quantum computing on established industries. The mention of applications in logistics and supply chains suggests that rather than being a niche field, quantum computing's advancements through error correction could disrupt established industries. This counters the intuition that quantum computing will only serve specialized sectors, indicating a broader potential for transformation across various domains. By examining these counterintuitive aspects of the implementation plan for 4D error correction codes, we gain a deeper understanding of the potential implications and transformative power of this project in quantum computing and beyond. In examining the report on the implementation of 4D error correction codes in quantum computing, several crucial elements may go unnoticed by the general audience, yet they hold significant implications for the project's success and the future of quantum technology. 1. The role of 4D error correction codes. While error correction in quantum computing is a widely acknowledged necessity, the specific focus on 4D error correction codes is a pivotal aspect that deserves closer attention. Most discussions around quantum error correction tend to emphasize the more established methods such as surface codes or concatenated codes. The introduction of a 4D framework may offer enhanced capabilities in dealing with higher dimensional error spaces, which could lead to more resilient quantum systems. Significance. The complexity of quantum states means that traditional approaches may struggle with the types of errors experienced in practical quantum computing applications. 4D codes could allow for greater fault tolerance and efficiency, which are critical for achieving scalability in quantum systems. Overlooking this aspect might lead to underestimating the potential impact of this project on future quantum applications. 2. Collaborative network with universities. The report highlights collaboration with 8 leading universities, emphasizing a multidisciplinary approach. This collaboration is not just a means to share resources, it represents the fusion of ideas from different fields such as physics, computer science, and applied mathematics. Each institution will likely bring unique strengths, methodologies, and perspectives that can enhance the project's outcome. Significance. The effective integration of diverse academic insights can lead to innovative solutions that a single institution may not achieve in isolation. This network could accelerate the pace of discovery and application, making it crucial for stakeholders to follow the dynamics of this collaboration closely. Ignoring the collaborative framework may result in underappreciating how collective expertise can drive breakthroughs in the project. 3. Phase-specific goals and timelines. The report outlines clear phases of development, but the importance of these milestones is often underestimated. Each phase serves not only as a checkpoint for technical progress but also as a strategic opportunity for stakeholders to reassess, pivot, or scale their investments based on findings. Significance. The timeline from theoretical research to prototype development and then to full-scale implementation reflects a structured approach often seen in successful tech ventures. By sticking to these phases, the project can systematically address potential pitfalls before they escalate. Stakeholders should remain engaged through each phase, as the outcomes at each stage will inform the next steps and investment decisions. 4. Potential use cases and applications. While potential applications are mentioned, the depth of their significance can be overlooked. Areas like quantum cryptography, advanced materials modeling, and optimization in logistics have transformative potential. The practical implications of deploying 4D error correction codes could revolutionize sectors from cybersecurity to pharmaceuticals. Significance: the ability to demonstrate actual use cases can attract further investment and interest from industries that stand to benefit. By focusing on concrete applications, the project could secure partnerships and funding that extend beyond the initial $5 million budget. Not recognizing these potential avenues for real-world impact may hinder broader engagement and support. 5. Budget allocation and resource management. The reported $5 million R&D budget may seem substantial, but the efficient allocation of these resources is critical. The challenge lies in balancing theoretical research, prototype development, and testing, each of which requires a different focus and resource commitment. Significance: the success of the project hinges on prudent financial management and prioritization. A detailed understanding of budget allocation can provide insights into the project's feasibility and longevity. Stakeholders should scrutinize resource management strategies to ensure the project remains on track and can adapt to unforeseen challenges. 6. Addressing noise and interference. The report mentions the susceptibility of quantum systems to noise and interference but does not delve deeply into the implications of these challenges. Quantum computing operates in environments where external factors can significantly impact performance, and the ability to effectively mitigate these issues is essential for practical applications. Significance: understanding how 4D error correction codes can address these challenges is vital. Those involved in the project or considering involvement should recognize that advancements in noise mitigation are as critical as improvements in computational power. The interplay between error correction and environmental factors can significantly influence the project's outcomes and its broader applicability. 7. Long-term vision beyond 2024. The report focuses on the immediate goals set for Q4 2024. But it does not explicitly address the long-term vision beyond this timeline. A lack of foresight could lead to missed opportunities for subsequent phases of research and development. Significance: establishing a long-term roadmap that includes post-2024 objectives could help maintain momentum and ensure continued investment. Stakeholders should be aware of the importance of planning for sustainability and scalability in technology projects. A clear vision beyond the initial implementation phase can help secure ongoing support and drive future innovations. Conclusion: the implementation of 4D error correction codes in quantum computing represents a significant leap toward addressing some of the most pressing challenges in the field. However, various aspects of the project, such as the specifics of the 4D framework, the collaborative nature of the initiative, the structured phase approach, and the potential applications, are often overshadowed by the more general discussions surrounding quantum technology. Recognizing and emphasizing these elements can enhance understanding and engagement with the project, ultimately contributing to its success and the transformation of quantum computing. 1. Phased implementation strategy. The project is structured into 3 clear phases: research and development, prototype development, and full-scale implementation. This phased approach is crucial as it allows for systematic progression from theoretical foundations to practical applications. Each phase builds upon the previous one, ensuring that the development of 4D error correction codes is grounded in thorough research and testing. This structured methodology is essential for managing the complexities associated with quantum computing and error correction, enabling focused efforts on achieving specific milestones. 2. Collaboration with leading universities. the involvement of 8 leading universities showcases a collaborative model that leverages diverse expertise in quantum physics, computer science, and applied mathematics. This collaboration is valuable not only for the pooling of knowledge but also for fostering innovation through interdisciplinary approaches. The universities can provide cutting-edge research, access to advanced technologies, and a fresh perspective on challenges. Such partnerships are critical in addressing the multifaceted challenges of quantum error correction, enhancing the project's potential for success. 3. Potential applications of 4D error correction codes. The project outlines several promising use cases for the effective implementation of 4D error correction codes, including advancements in quantum cryptography, materials modeling, and optimization problems. These applications highlight the transformative potential of improved error correction in quantum computing, as they suggest significant improvements in security, efficiency, and problem-solving capabilities across various industries. Understanding these applications is vital for stakeholders to appreciate the broader impact of the project and its alignment with industry needs. 4. Significance of error correction in quantum computing. The emphasis on error correction as a critical component of scalable and reliable quantum systems cannot be overstated. Quantum computers are inherently susceptible to errors due to decoherence and noise. Therefore, developing robust error correction codes is essential for making quantum computing practical for real-world applications. The project's focus on 4D error correction codes represents a significant advancement in addressing these challenges, enabling more reliable quantum computations and paving the way for the future of quantum technologies. This understanding is crucial for stakeholders in both academia and industry as they consider the implications of quantum advancements. Here are 3 famous historical cases similar to the content of implementing advanced error correction codes in collaborative research in the field of quantum computing. 1. The Human Genome Project (HGP). Overview. Initiated in 1990 and completed in 2003, the Human Genome Project was an international scientific research initiative aimed at mapping and understanding all the genes of the human species. It involved collaboration among multiple institutions and universities worldwide with a budget of approximately $3 billion. Key phases. The project was executed in various phases, including the mapping phase, sequencing phase, and data analysis and interpretation phase. These phases were marked by extreme collaboration across disciplines including genetics, bioinformatics, and computational biology. Impact. The successful completion of the HGP has had profound implications for medicine, biotechnology, and genetics, leading to advancements in personalized medicine, genetic testing, and our understanding of human biology. 2. The Apollo Program. Overview. Launched in the early 1960s by NASA, the Apollo program aimed to land humans on the Moon and bring them safely back to Earth. It involved extensive collaboration among NASA private contractors and academic institutions with a budget of over $25 billion in 1960s dollars, equivalent to over $150 billion today. Key phases. The program consisted of multiple phases: unmanned test flights, manned missions Apollo 1 through Apollo 17, and lunar missions. Each phase required rigorous testing, development of new technologies, and integration of diverse scientific and engineering expertise. Impact. The Apollo program not only achieved its goal of landing on the Moon in 1969 but also significantly advanced technologies in computing, materials science, and telecommunications, laying the groundwork for future space exploration. 3. The Manhattan Project. Overview. During World War II, the Manhattan Project was a secret U.S. government research project aimed at developing atomic bombs. It was a collaborative effort involving scientists, engineers, and military officers with a budget of approximately $2 billion, around $30 billion today. Key phases. The project had several critical phases, including research into nuclear fission, the development of various bomb designs, and the construction of production facilities. Collaboration was key, with significant contributions from universities and research institutions. Impact. the successful development and deployment of nuclear weapons had a profound effect on the outcome of World War II and subsequent global politics, leading to the Cold War and ongoing discussions about nuclear energy and weapons. These cases illustrate the importance of collaborative research-phased development and the integration of advanced technologies, similar themes present in the implementation of 4D error correction codes in quantum computing. Future outlook: predictions for the implementation of 4D error correction codes in quantum computing. Overview. As we approach the end of Q4 2024, the implementation of 4D error correction codes in quantum computing represents a pivotal moment in the evolution of this technology. This initiative, supported by a $5 million R&D budget in collaboration with 8 leading universities, is expected to not only enhance the reliability of quantum systems but also set the stage for significant advancements across multiple sectors. Here we delve into predictions regarding the future impact and developments resulting from this project. Predictions for quantum computing advancements. 1. Enhanced error correction mechanisms. By successfully implementing 4D error correction codes, we anticipate a transformative improvement in error rates within quantum systems. Current quantum computers are limited by their susceptibility to noise and decoherence, which can lead to inaccurate computations. With robust error correction methods in place, we expect a substantial increase in fault tolerance, enabling quantum computers to perform more complex calculations reliably. 2. Mainstream adoption of quantum technologies. The advancements stemming from this project are likely to accelerate the adoption of quantum computing across various industries. As the technology matures, sectors such as finance, pharmaceuticals, and logistics will begin integrating quantum solutions into their operations. This trend could lead to a competitive edge for early adopters who leverage improved computational capabilities for optimization modeling and simulation tasks. 3. Breakthroughs in quantum applications. With enhanced error correction codes, we foresee breakthroughs in applications like quantum cryptography, which will become more secure and robust against attacks. This will not only bolster data security protocols but could also pave the way for revolutionary advancements in secure communications and transactions. Additionally, industries focused on drug discovery and materials sciences may achieve significant milestones through advanced simulations enabled by quantum computing. 4. Collaborative innovations and knowledge sharing. The collaboration with 8 leading universities will foster a vibrant ecosystem of innovation. We predict that this partnership will lead to the development of new theoretical frameworks and experimental techniques, further enriching the field of quantum computing. Knowledge sharing among academic institutions and industry partners will create a continuous feedback loop, driving further research and application of quantum technologies. 5. Educational advancements in quantum computing. As the project unfolds, we expect an increase in educational initiatives focused on quantum computing, driven by the collaboration with academic institutions. Universities may introduce specialized programs and courses aimed at equipping the next generation of scientists and engineers with the necessary skills to work in quantum technologies. This educational push will be crucial in building a workforce adept in quantum theory and practical applications. 6. Increased funding and investment. The successful demonstration of 4D error correction codes is likely to attract further investment in funding into quantum computing research. Venture capital firms and government initiatives could ramp up financial support, recognizing the potential economic impact and innovation arising from quantum technologies. This influx of funding will enable ongoing research development and commercialization of quantum solutions. 7. Regulatory and ethical framework development. As quantum computing technologies become more integrated into everyday applications, there will be a growing need for regulatory and ethical frameworks. We predict that stakeholders will collaborate to establish guidelines governing the use of quantum technologies, particularly in areas like data privacy and security. This regulatory landscape will be essential in ensuring that advances in quantum computing are aligned with societal values and ethical standards. 8. Interdisciplinary research growth. The complexity of quantum computing necessitates interdisciplinary approaches. We anticipate a rise in collaborative research that combines insights from physics, computer science, engineering, and mathematics. This interdisciplinary focus will not only drive innovation but also enhance the understanding and application of quantum principles across diverse fields. Conclusion. The implementation of 4D error correction codes in quantum computing by the end of Q4 2024 marks a critical juncture in the evolution of this groundbreaking technology. The predictions outlined highlight a future characterized by enhanced reliability, broader adoption, and transformative applications across various sectors. With collaborative efforts driving innovation and education, the next few years will likely see quantum computing transition from experimental phases to practical widespread use, ultimately reshaping industries and society at large. As we move forward, the lessons learned and advancements made in this initiative could set the foundation for a new era in computational technology, paving the way for a future where quantum computing is an integral part of our technological landscape.